Okay, well, welcome back. Thank you for showing up again. This will be our second lecture for dynamic network modeling. Today, I hope we'll get to some simple population models of epidemics, SI models, and possibly some SIR models. I thought maybe we could start by just going over the topics. We're going to be asking you to do a little introduction of yourself, just a few words so that everybody in the class knows where other people are coming from. Maybe you're all from the same class this year, but sometimes there are people from different departments or different years, and so it's helpful to have some of that. So that's why I'd asked people to log into the Zoom even if they're in room. And then I want to talk a little bit about some organizational things about the class project, because I know we have to get that started pretty soon. And then we'll cover some material that originally I thought we'd cover perhaps last week on using Tellurium modeling. And then we'll jump into modeling epidemics. So maybe we could just start by having people introduce themselves very briefly. I have three people here. I don't know if you'd like to just tell us in a few words what class you're in, what you're studying, and anything else that might be interesting to the other people in the room. Can I ask people to introduce yourself? Start there.
Can you hear me on Zoom?
Sounds okay to me.
I'm Drew. I'm a senior in ISE, and
Hold on a second. I got to mute my mic. Go ahead.
I'm a senior in ISE. Still. Okay. I'm a senior in ISE, and what should I say for interest? Just I don't know. I'm in the bio track, so I've been doing research and simulations of like cell tissues already. So yeah.
That didn't work remarkably well.
My name's Colin. I'm a senior on the ISE major track in the bio department also. And I've also been working on some cellular modeling based projects mostly. And on the 5 years Masters in Science program here.
My name is Ryan. I'm doing my second semester in the ISE program. And right now I'm working with modeling biological, working on biological models. Interesting thing about me, I'm also doing like a backpacking course this semester.
I'm Ben. I'm a third year data science student, undergraduate. Yeah, I don't know if there's anything else about me to know.
I already went, sorry.
Okay, sorry. Let's see, who haven't we heard from?
I can go.
Okay, done.
My name is Delaney. I'm a senior in ISE, and I was pre-med my first year, but I switched over, so I'm technically a junior, but in ISE. Interesting thing about me is I have two cats, one of them right here, and the other one running around somewhere. But yes, that's me.
Okay. When I lecture from home, I often wind up having a cat in the picture too. Okay, who's next?
I can go. Can you guys hear me okay?
Yep, that's fine.
My name is Ali Godfrey. I am a junior studying intelligent systems engineering with undergrad with the bioengineering concentration. I haven't really done too much, within that concentration quite yet because we're just now allowed to take bioengineering related classes, but I'm interested in like genetic and tissue engineering, particularly, I think. I don't know. A fun fact about me, I have a twin anyway, so we don't look alike, so yes.
Okay, well, great. Let's see, who have I missed? Anybody that's been missed? Or did we get through everybody? Giuliano, maybe you could introduce yourself.
Yeah, sure. Hello, everyone. I'm Giuliano. I'm a fourth year PhD student with James. I've been doing biological tissue modeling during my PhD, and I also did less biomodeling before, but I modeled cellular structure still. And I'll be helping out with the class during the semester.
Okay. PJ, you don't have to introduce yourself, but you're certainly welcome to if you want.
Sure. Yeah. Hello, everyone. My name's TJ Sego. I'm a postdoc. I also work with James. I do a lot of modeling and software development. I'm the lead developer of Computational. So get anywhere near that territory and you have some specific technical issues or need some help with putting together models, feel free to reach out to me. I'll put my email in the chat just in case. Thanks.
Okay, did I miss somebody or is that everybody? Okay, thank you. So we've got a mostly ISA group, some people from data science, and different levels of experience with modeling as usual. As I've said before, everybody who comes here pretty much has some strengths and some gaps in their education. And so please try to help work together to fill in for each other. Usually it's a pretty collaborative environment. So let's see if I can get this to work now. So I'd like to talk just a little bit about the semester projects. Would it be better if I turned the lights off in here? I don't know if you're looking on your laptop, it probably doesn't make any difference. If you try to see this, it's okay. Whichever. No opinion. Okay, so I'd like to talk to you a little bit about the semester project. I asked people for this week to look at one paper that they thought was interesting. For next week, I'm asking you to pull together a slightly longer list of possible papers to consider. And then I'd also like next week for you to, of those longer lists, to pick maybe 2 or 3 and then do a short analysis of them that you could present to the class that you could then begin to think about working up to a preliminary project proposal. And the idea for this is not to torture you, but rather to help you start thinking about what you'd like to work on. And so you are certainly free to pick papers that are in different areas if you're thinking about possibly working in different areas. You're certainly also free to change your mind afterwards and do something else. But I wanted people to start doing a little bit of reading around and research to think about what was interesting to them. And to get you started, we sent a list of about 20 or so possible papers on a whole variety of subjects. Those weren't meant to be by any means exclusive. By all means, look around and find things that aren't on that list, but it was some possible things that could have been interesting, either things people have typed as papers in the past or things that we've worked on or thought would be interesting. And the goal here is that if you pull together a few papers that could be things that you might use for your project. And also the reason I'm asking you to present them, and again, I'm not asking you to do a big presentation, just a little bit, is to see whether there's anybody else in the same class who's interested in the same thing. Because as I say, you're welcome to work on your own, but it's easier for you probably to work as a team, and certainly reduces your workload. And if there is somebody else who shares the same idea, it can be very helpful. And also, it avoids the situation where you have 7 people who each work on exactly the same paper and do an independent report on it, because that's fine if that's what you want, but it sort of maybe not doesn't maximize the impact. So again, we set a preliminary list around with some topics. I know it can seem intimidating to say find 5 or 10 papers. Google Scholar is a great place to start, but one of my former students, who's now a professor at Georgia State, wrote a rather nice introduction to thinking about how to look at papers. And her point was that, to decide whether you're interested in a paper, you don't have to read the whole thing from beginning to end. If you're scouting a paper, of course, the abstract is designed to give you an overview of the paper. If the abstract sounds totally boring, it's probably not worth going further. The introduction should give you, at least at the beginning, some background material that might give you some orientation about it. And I certainly find that somebody in my world, figures are very communicative. And often if the figure captions are good, you don't even need to read the paper in detail to get an understanding of what it's about. Sometimes a striking figure is enough to decide you about whether you find it interesting. Once you've got your long list down and you're beginning to think about papers that you might more seriously work on with the class, I would suggest looking at the method section. And this is something that may or may not be easy to do depending on your background, and I can certainly help out with it, which is to look at the method section and see whether it's something that you could actually do in the class. So this class, we're going to be using Animony. And Animony is a great language for writing models very quickly in a compact way, but it does have some limitations. It can represent certain kinds of models, that is, models that are written in the form of rate equations. If the paper is about a spatial model with agents, this is not the class for that. We teach that next semester. If it's a rules-based model, or if it uses complicated integral differential equations for populations, then those are not very convenient to represent with Animony either. And so they may not be such a great fit. They're good if you're doing Python generically, but they're not so useful in this context. And so you might want to take a quick look at veto papers that seem to be fascinating, but just out of scope. As you don't want to make yourself life. I rarely will tell somebody that they can't work on a project, but sometimes people get exceedingly ambitious, and I try to steer people away from projects that are going to take them more than the time they have. Yi has some criteria for deciding whether papers are good enough to be worth looking at seriously, because a lot of what you're going to be doing is spending time replicating the paper's results. Well, if the paper itself isn't of very high quality, you could be spending a lot of your time and effort reproducing something that's not very exciting. And sometimes there are signals like, is it a good journal or not that it's published in? Of course, a lot of good papers are published in not so famous journals. A lot of so-so papers are published in famous journals. If you know the field, sometimes you know the people who are doing exciting work, but again, sometimes people you've never heard of do great work. sometimes people who you've heard of don't do wonderful work. But more to the point, when you're looking at a paper, you might want to ask the question, does it actually do what it says it's trying to do? If it says, we're going to show you the effect of vaccination on strategy, on outcomes in the disease, does it actually do that? And if you're interested in a particular topic, a research problem, especially if it's not your primary paper, but a secondary paper, you can ask whether it's giving you information or whether it does something you care about. There's also a sanity check. I mean, most refereed papers, somebody's looked at them and said that they're not crazy. But once or twice in this class, I've had students who picked a paper that looked pretty decent to begin with. And when they dug into it, they found out that the results that were presented weren't right. I've had students who've actually caught published papers that were incorrect. It's great when students are able to do that, but it's also a lot of extra work if you do that. So it's good to ask the question, does it make sense? Is it reasonable? Does it seem to be carefully written? If it's a modeling paper, mathematics paper, do they provide enough detail to evaluate whether they did it right? If it's a modeling paper, do they explain why they made the choices that they made? And then how generalizable is it? Is it something that you could apply more broadly, or is it something that's very, very specific? And then if it uses a methodology that you find interesting, you can ask the question, is it something that you could apply for your particular problem? And then the question, which is the one I alluded to earlier, which is, do the methods require specialized software? In general, we're planning on using this simple modeling framework, and so we want to find things that can be represented in it. If you're planning specifically on reproducing it, you want to know, is it explained well enough to reproduce it? And you would, this is a problem that comes up a lot in experimental biology. Reproducibility is not trivial. A lot of famous experimental biological papers were never reproduced. You would think that perhaps that with programming, if they give you a list of a listing of the program they used, that you'd be able to reproduce the paper. In fact, reproducing modeling papers is non-trivial as well. And so you want to make sure that the information is there. For next week and the week after, you may not be in a position to read it in enough detail to be able to do that. But I can promise you that we've had experiences, not only in the class, but also in our research, where we've seen a paper that was really very interesting, great results, fascinating problem, interesting methodology. And you say, I should be able to type that up in our modeling framework and reproduce their results. And when you start typing it up, you realize that they didn't give the parameter values for their simulations. So you're stuck. So I don't, sometimes those things are mines that are hiding, waiting to blow you up later. But we want to avoid people stepping on mines if we can. And so the more information they provide, both about the modeling approach and what they did to do the specific studies they did, the better. And then in terms of interpretation, do they actually give you enough context that if you're going to create, remember your job here is not just to write a review or a paper, it's to create an application that other people will use. And so you want to think about whether you have enough context for it, that if you're writing a report, that somebody who's coming in from the outside and looking at that report will say, wow, I want to work on that. And sometimes they don't. In mathematics journals, it's pretty common to start seeing paper which says title of paper, author, and then first line of paper, theorem 1, for all the those papers may be making great technical advances, but if you're not a specialist, you're not going to understand what they're about. And so I personally feel that it's very important to try to explain things in a way that people will be able to, at least, even if they're not a specialist, they should be able to read the first page and understand why you did what you did. And especially because if you're reproducing a paper, starting from a single paper, I'm going to ask you to try to do at least a small extension of it. You might look at the last paragraph and ask the question, are there discussions of the limitations of what they did, of problems with what they did, of ways that you could extend what they did to make it more comprehensive? Those could be really helpful when you're designing a term project. If you're looking at experimental papers, you can say, why are we looking at experimental papers if we're doing a computational project? Well, ultimately, models are about reproducing things in the real world. And so you'd like to be able to have some kind of experimental data to compare your model to. In many experimental modeling papers, they'll give you the experimental data in the paper, but not always. And so it's useful, for example, suppose that you took a paper on how interferon changes the way the virus propagates in your lungs. You might have some experimental data in the paper, but somebody else might have published an experiment where they did interferon treatment. And you could then try to take that additional experimental data and use it to test your model. And so there are a lot of things that you might want to have from an experimental paper. Experimental papers often do a better job of explaining the biological context of the problem than the modeling papers. And so you could ask the question, what kinds of things could be in an experimental paper? Background information, lists of components, lists of what's happening, diagrams, hypotheses you could test. And so it's actually a useful exercise to look for experimental papers that are related to the topic that you want to model. Of course, if there aren't models, then all you have are the experiments, so then you have to think about how to build the models based on the experimental paper. And again, some experimental papers are sort of very easy to translate into models, others are not helpful that way. So I recommend thinking about it. Okay, so I wanted to give you a little bit of background on that reading and writing assignment. Again, what I'll ask you to do is pick 5 to 10 papers. I just write 1 or 2 sentences about each one about why it's interesting to you. And then I'd like you to pick 2 or 3 of them and dig in a little bit with these questions that we have. Again, not much. I mean, maybe 4, 5, 6 sentences, a couple of bullet points. And then in class next week, we'll take a half an hour and have people take those couple of bullet points. You can put them on a PowerPoint slide or just in a Word document and show the class what the paper was, tell us a few words about why it's interesting, and analyze a few of these issues. And that way you can see if there's some overlap or interest, shared interest. Are there any questions about that as an assignment before we move on? So last time, I'm going to go over, the introductory classes always tends to be a little bit too fast, and also sometimes people are thinking of other things. So I'm just going to review some of the things we covered last time. Again, in this class, we're primarily going to be using Tellurium. There's this nice online resource plus the handouts that I gave you. And then Tellurium works in conjunction with Python. And so you'll be using some simple NumPy methods to plot things, do data analysis, and so on. If you haven't used NumPy before or SciPy before, the best thing to do usually is to search, how do I do X in Python? And Stack Overflow will usually pop up an answer for you. There's also that Python cheat sheet that we handed out that gives a pretty good list of the basic things you want to do. And I'll point out that the Python that I'll use in class is not always the most elegant Python possible. Python is a very large and elaborate language, especially with NumPy extensions. And so there often may be faster and more elegant ways to do things than the ways I'm going to do them. And if people have good ways of solving problems that are simpler than the ones I'm going to show you, please bring them up. And we talked about networks as a concept and how many different fields and areas networks come into. We looked at some of the different kinds of biological networks that exist. Again, in this class, we're primarily going to be talking about, to begin with, about epidemic networks, viral transmission networks. We're going to talk also about what are called population dynamics networks, which is how the virus spreads and how the body responds in the body. If we're talking about immune response, we'll get into signaling networks. We're going to do maybe a little bit on drug treatment, in which case we'll talk about physiologically based pharmacokinetic networks. All of these networks have fundamentally the same architecture and can be described in the same mathematics. We also just introduced the very abstract concept of a model and what a model does. So a model is essentially a black box. It takes as an input a set of model structures. That could be something like the network architecture that we have. But a set of parameters that could say quantify the rate laws and initial conditions. And that gives us as an output some set of output metrics. Typically, in our world, those are going to be time series of amounts of something or concentrations of something. Sometimes we're going to be interested in how much the total area under the curve is of something. Sometimes we're going to be interested in the final value of something. Sometimes we're going to be interested in the whole details of the time series. And it's going to depend on the question being asked and the context. We've seen pictures of networks. Networks have a fundamental architecture. That architecture consists of nodes connected by links. Those links in our world are typically going to be drawn as arrows of one sort or another. That set of nodes and links has a topology. It has an architecture. And that architecture then is going to describe how the state living in each node influences the state at other nodes. And in the case of dynamics, we're specifically interested in how the states on the nodes change in time. We are going to be using primarily Tellurium on NanoHub, although Tellurium will run fine in any Python IDE. So if you have a desktop version of Jupyter Notebooks, you can certainly use that. And remind you that we were using how to get into Tellurium. I hope by now you bookmarked that page and remember how to launch the tool. So we're going to be doing that. There's this one annoyance that we run into immediately with Delirium on NanoHub, which is that when it first opens, the notebook that you're going to have is not editable. It's going to be, if you open a notebook by itself, it'll be read-only. And so you have to then go into the file menu and create a new notebook. And then you have to retype in that import Tellurium with PE line. If you don't do that and you create a non-editable notebook, it's not the end of the world, but you don't want to wind up accidentally losing the code you've been writing. So that's something we have to remember. We'll typically also use NumPy, so I almost always will do import NumPy as NP as well, so it's available. I put the simulations that we're going to be running. In general, we'll try to do the simulations in a way where you develop them yourself in the class, but in case people get stuck, so you don't get too frustrated, I'll typically give you a solution to the problem. Those are my solutions. That doesn't mean they're the only ones that are right or even the best ones. I'd ask you probably, unless I ask you specifically to upload the solution first, to try it yourself before you jump to the solution. Depending on whether you have Google Drive running on your computer, if you have Google Drive running on your computer, you should be able to upload the simulations to NanoHub directly from my Google Drive that I've shared with you. If you don't have Google Drive running on your computer and you're using the web interface, you'll have to download it to your local computer and then upload it to NanoHub. And if you go to the Open menu in NanoHub, it'll pop up an upload window. You can then browse in the upload window for the thing that you're looking for and hit upload. So you actually have to upload twice to get it to upload. And I've shared the Google Drive before. Does anybody need the link to that Google Drive again? They're also, we'll try to put all those models up on Canvas as well, so that you can download them from Canvas if you don't want to use the Google Drive. If anybody needs the Google Drive link, let me know. All right, so now let's come to the first exercise, and this is walking us through the syntax of Tellurium. Almost all of our Tellurium models will look very similar to this. They'll be longer, they'll be more elaborate, but structurally they're not going to look very different. Every Tellurium model is going to consist of two things. It's going to consist of some Python code, and it's going to consist of basically a character string that specifies the model. And one of the things that we have to remember when we're using Tellurium is that it's what's called the declarative language, as opposed to procedural language like Python, which means that it doesn't necessarily execute line by line in sequence. You'll find out that in Antimony, the language, you don't have loops, for example. You don't have conditionals. So the concept of order of execution is there only in a limited way. And this really is a model specification. And we'll come back to what that does and means in a minute. So we're always going to have to import Tellurium as TE. That gives us access to the Tellurium library that we're going to be using. You could import it as something else. You can name it anything you want, but you need to have those functions available to us. And then typically there'll be this thing called model string. And we usually use triple quotes to allow us to have carriage returns in it. And that model string will consist of your model specification. And so the model is actually written then inside the string. One consequence we're going to find out is that when there are errors in the string, it doesn't point to where the error is, which is sometimes a little bit annoying. So the first thing we have to do is load the Tellurium, which is that import Tellurium as TE. Then we're going to define our Antimony string. And again, you don't have to use triple quotes, but if you use carriage returns inside of a string, you have to have the triple quotes in Python. And you could use either triple apostrophes or triple double quotes, either one. You just have to balance them on the beginning and end of the string. So the next thing is that the syntax for Antimony isn't quite matching that of Python. It uses the double slash as the comment character instead of the Python hash sign. It uses the semicolon, which is sort of a C++-y thing to do, as the separator. You'll see a lot of semicolons. A semicolon at the end of a line is optional, although I tend to use them anyway. But it's a delimiter. So in principle, I could have taken out all the carriage returns and just written after the semicolon, deleted the carriage returns and made this one huge long line if I wanted to. All right. So PowerPoint has decided not to behave. I apologize for that. That seems to be a Zoom issue. So Animony was originally written, designed to write chemical reactions. And so its fundamental way of specifying a model is with arrows. And so if I think about a chemical reaction, in this case, it's actually an infectious process. P here, the number of uninfected individuals, goes to I1, the number of infected individuals, is the rate beta TV, where V is the amount of iris. That's translated into antimony in the following syntax. We optionally name the reaction, and it's good practice always to name it. Here we've named it E1. The name could be anything, it's arbitrary as long as it's not a reserved word. E1 and then a colon rather than a semicolon. And then exactly that arrow, T goes to I1. And then since we can't write the rate law as a superscript, semicolon, and then the rate law, beta times V times T. And end the line with a semicolon. The difference between writing it this way and writing ODEs is that one equation takes care both of the decrease of T in time and the increase of I1 in time. And so that one line with an arrow generates two equations. And if I had 5 different variables on the left-hand side of that E1 equation and 4 on the other, it would generate 9 equations. And so this is potentially a very compact way of writing networks. This time, this one worked, so we can see it. Okay, so again, we write the arrow diagram, T goes to I1 at a rate beta PV, and then we type that in Animony. The name, we'll call it rate law 1, E1, colon, T goes to I1, semicolon, beta times T times V. And so if you've got an arrow with a rate sitting on top of it, converting it to type is extremely simple. And that's really the whole point of Antimony, is that simplicity. Of course, in the real world, our rate laws are going to be more than one reaction, but fundamentally, it doesn't get much harder than that. As I mentioned, Antimony was designed to do chemical reactions, and chemical reactions usually have multiple components on both sides, and they may combine in particular ratios, what's called stoichiometry. You might have 3 molecules of A combining with 5 molecules of B to make 1 molecule of A, 2 of C, and 9 of D. And so if you wanted to write that as a bunch of ODEs, well, the ODEs are down here. You have 4. 1 for A, 1 for B, 1 for C, 1 for D. And you have to write the rate terms for each one of those separately. In Antimony, that whole chemical reaction turns into a single line. If you combine 3 A's and 5 B's together, you write 3A plus 5B. It goes to here, A plus 2C plus 9D. What you'll notice is special in Antimony in terms of syntax is that if you're specifying the number of individuals that are combining in a given process, 3 A's and 5 B's, you don't write the times. You don't write 3 times A plus 5 times B. You really write the number 3 or number 5. We're not going to use that so much early on in the class, but later on, when you get to more complex in-host responses, you'll need that. The other thing to remember here is that Python and Antimony aren't the same for exponentiation either. Antimony uses the caret as opposed to the double star for exponentiation. You can also write EXP parenthesis, value comma value, if you want exponentiation. There are a lot of predefined functions in Antimony, and so you can look in the manual and the handout for some of them. We're not going to use a lot of complicated ones, but basic things like basic trigonometry are also applied. One thing that we're going to find pretty useful is the idea of sources and sinks. Suppose that you have this could be a chemical concentration, or it could be a population. And suppose you're adding the chemical to a dish, or people are being born. In that case, you have an arrow coming from nothing pointing at A. and you have the rate law sitting on top of it, just the way you would otherwise. So nothing goes to A at a rate K, generates the differential equation, dA by dt equals K, constant increase. You could also write a sinc term where A decays to nothing. Typically, that's what's called first order kinetics. The rate is K times A, it's exponential decay. In both cases, you write exactly what the arrows say. E1 colon nothing, arrow goes to A, semicolon K, or A goes to nothing, semicolon K times A. And so you're allowed to do that. Something that you use quite a bit in chemical reactions that we're not going to use so much here is what's called the boundary species. Sometimes you want something to look like a variable, the amount of A, but you don't want it to change in time. And if you put a $ in front of the variable name, then A is defined to be fixed in time. We'll come back to that when we need it. We can write ODEs directly, first order ordinary differential equations. We use apostrophe to do that. T apostrophe equals beta times T times V. We'll generate dt by d capital T by little t equals beta TV. That's functionally equivalent to writing nothing goes to T at a rate beta times T times V. They both generate the same thing. Sometimes if that's convenient, on the other hand, typically you're going to wind up writing twice as many equations if you do it that way. If you're used to writing ODEs, it may take a little bit of practice to get used to writing them in terms of arrows, but in the long run, you win. If you have the same variable repeated multiple times, all of the rate laws sum together. So if I have nothing goes to T at a rate K0 and T plus V goes to I1, then I'm creating T at a rate K0 and I'm destroying it at a rate K1 times T times V. So if I wrote an ODE for T, I'd have the sum of those two things. D capital T by D little t is equal to K0 minus K1 times T times V. And that's, again, something that you wouldn't necessarily expect if you were thinking about this in a procedural form rather than a declarative form. And so in this case, these three rate laws that I've written here, the creation of T, the combination of T and virus to create infected individuals, and the disappearance of the infected individuals generate four ordinary differential equations. So any variable that's on that left-hand side of either side of an arrow is a variable. K1 and I1 are K1 and K2 are rate constants. When we specify a model, it's required that we specify all of the parameters in a model. So if we have T goes to I1 at a rate beta times T times V, we have to tell it what the value of beta is, or it will complain. We should also tell it what, we also have to tell it what the value of V is, because those are both parameters. We should tell it what our initial values of T and I1 are. If we don't, it will assume that they're zero. But it's safer always to have every variable and parameter defined in your model. And we're going to find that we can change those things quite easily from Python. So now we're going to specify the initial conditions. And I have here something that is convenient to do, but could cause some issues later on, which is I've set a variable T0 equal to 1 e to the 7th. And then I've set my initial value of T equal to T0. And in a procedural language, that's not confusing. T0 is given 1 e to the 7th. At the line after it, T equals T0 assigns T a value of 1 e to the 7th. we're going to find out in a few minutes that that has some interesting effects. And we have to be aware of those. All right, this line is out the highlight is slightly out of line here. The next thing that we have to do now is specify our antimony string. Is we have to take that antimony string and we have to convert it into something executable. And there's a method in Tellurium called TE load A, which operates on a string and returns an executable object. And so M equals TE dot load A of model string takes model string, it parses that model string and converts it into an executable. And what's important is that that parsing, that interpretation of the model is done only then. It's only done once when you load the model. And that means that you don't have you're not going to go through and execute that model sequentially. The only thing that's sequential is the way the parser reads the model. Once that model object has been created, we can execute it. And the typical function we're going to use to execute it is simulate. M.simulate, in this case, applies the simulate operator to, simulate method to M, the parsed model, the executable model. And it has typically 3 arguments. There are other arguments you could give it, which we'll talk about later. The initial time we start the simulation, the final time of the simulation, and how many steps we're going to use to do the computation. Typically, it uses a forward method, and so you're going to specify how many steps. You don't have to specify the number of steps, and it'll try to guess it and use other. It has a variety of numerical solvers that are available. That will then return an object which consists of the results of the simulation. Those results have a somewhat complex form. It's not a simple NumPy array. In particular, the names, the alphanumeric names of each variable are present at the top in a header line. So this looks more like an Excel spreadsheet than a simple Python array. And so the first column from M.simulate is the time. The second column would be the first variable that you're creating. The second column would be the second variable that you're creating. And so when you're going to manipulate S, you have to be aware of the structure of that object. There are a variety of ways of plotting things. If you're just starting out, the simplest one is M.plot. Plot is a predefined function in Tellurium that knows how to handle that object. The simulate object, the object returned by simulate, and it'll generate an auto-scaled plot with time on the x-axis, the values of your variables on the y-axis, and a little inset key with the color-coded variable names, like that. That looks great if you're only plotting 2 things. If you want to do something more sophisticated, typically we have to use essentially matplotlib functions to do things. And in that case, sometimes having this slightly more complicated object structure is a little bit of a pain because we have to do a lot of slicing. But you can actually, even in this simple predefined plot function, if you want, you can change the plot axes, the labels, the line widths, and so on. One thing we'll find is that the functions that you're given here for doing that are slightly different in the basic plot function from the ones in matplotlib, and that can be a source of small confusion. If people have memorized matplotlib options, you're better than I am. I always have to go online and look it up. All right. So last time we built a simple model, the one I just walked us through. And now I'd like to do a tiny bit of Python programming to show you how to combine Python and Tellurium together. And so what we're going to do is we're going to take that code and we're going to modify it to explore the effect of changing a parameter. And so-called parameter sweeps are something we're going to do a lot. And conceptually, in a parameter sweep, we're going to have to define a loop in Python that changes the value of the parameter that we're going to change. We have to learn how to change a parameter value in our model, which is very simple, but it's not something that is a Pythonic. It's a Antimony thing. Then we'll have to rerun the simulation, and then we'll have to display the parameters, the vector of the parameter change. And let me walk you through it, and then we'll do it again together. So here's the way to do it. Python has all sorts of iterators, and so you could do this in a fancier way, but this is a simple one. Let's suppose we're going to change the amount of virus in our simulation. And the thing that's going to be important is actually the second and third lines here. They're going to be the ones that are interesting. To begin with, we could just use the standard Python range function. So we'll say for p in range 0 to 6, which actually gives us 0, 1, 2, 3, 4, 5. That's the Python thing. The other thing is that I've never really understood why you had to go to NumPy to get iterators that aren't over integers. So I typically use NumPy arange, but we'll come to that in a second. The second line is that each time we're going to run a simulation, the basic concept in Delirium is that if I call simulate repeatedly, it doesn't restart the simulation. It continues it from where you were. So if I say simulate 0, 10, and then I call simulate 10, 20, it will continue the simulation from the final values that you had before. It doesn't reset them. And so if I want to start from the beginning again with different parameter values, I have to reset my simulation. I could do that by using that TELOAD again. That winds up being a slower operator. So there are a variety of reset functions. The standard one is m.resetAll that sets the variables back to their original values. Again, when you look at something like that, you'll see immediately that it doesn't look Pythonic. And if you're used to a procedural code, that looks rather strange. But that's how we're going to do it. The third thing, which is convenient, is how do we connect the parameters or variables that we specified in our Animony string with Python? And the answer is that those are all available as attributes of the loaded model. So if I've loaded my model and put it in with the handle m dot the variable name, or the m dot the parameter name, is that parameter value. So in this case, if I said the amount of virus in my model, I named the amount of virus v. If I say m dot v equals here 10 to the p, so that would give me 1, 10, 100,000, 10,000, 100,000. As I change the values of p, that will overwrite the initial value of v in my model. Then I run simulate, as usual. And now if I want to plot them on top of each other, there are a variety of ways I could do that. The quick and dirty way to do it is to use the m.plot, which is the default plotting program, with show equals false. Show equals false tells the plot to draw it in the buffer, but not actually put it up on the screen. And that'll cause the plots to overlay each other. And then when I'm done, I have to show that plot. So I use the PE method show to display the plot. So what I'd like people to do now is take, if I can get this to work here, take that example that we did last time. You could either retype it or you can do it by hand here. Sorry. I still have to get used to the fact that the mouse moves the opposite way of the way you expect from the screen. And I'd like everybody to do this little exercise. So this is our first real exercise. So you could certainly retype this. It might take a minute. I'd like people to type the code or use the code that we had from last time. That was model 1.1. And then add this parameter scan to it and see what happens when you run it. So why doesn't everybody take a few minutes and actually do that together? Is it clear what I'm asking you to do?
Yes.
And to begin with, I will ask people about how far they're doing, how it's going, and how far it's going along. But I'll use the poll here. When it looks like people have had enough time, I'll use the poll, and you can tell me if you're done or if you need more time. So you'll see that poll quite a bit. So I would ask everybody to do this, and I can do it. Do people need to see the old model to retype it, or does everybody have it? People who are online, I do have the chat window open. So if you type in the chat window, but you could certainly just unmute and ask a question too. But if you type in the chat window, I see that as well. And typically I won't launch that completion poll at the beginning, or if I do, you don't need to answer it until it looks like I'm about to move ahead to the next thing. And if anybody's having trouble finding the code or anything like that, let me know and I'll do my best to help out. This was our old simulation. I'll type while you're typing, I guess. Yeah. Somebody says you got an output and it's a mess of lines. Anybody else get output that's a mess of lines? See what I got. See where my cursor got to. Okay, so let me try executing this myself. That's what I got. Do other people get that? Oh, somebody should have spoken up. I've been talking as if you could see the screen and nobody could see the screen. People in the room could see the screen and not the people on Zoom. Sorry about that. So here I've been saying I was typing and you've not seen it. If I make that mistake again, please catch me. Okay. Everybody got that? Does anybody need help with it? Everybody okay? Yeah. Okay, so that's what I got when I did it the first time too. So that's not, as you say, that's not very pretty. And so that's one of the limitations of using this built-in plot program. It's not very flexible. And so one of the things that Tellurium allows us to do in that simulate method is we could use simulate to tell it which variables we want to output. And so in our case here, we actually only have two variables, namely t and I1. But if we type m.simulate, again, start time, end time, number of points between start and end time, and then comma, and then square bracket. So this is now a list. And we put the names of the variables in either single or double quotes. We list the variables that we want to plot. It then will only output the ones that we asked for. Okay. One thing that you can do is you can also output things that might not be so obvious. In particular, when we name a rate law like E1 colon T goes to T1, we can ask it to output the rates. So we can get the values of the derivatives as well as the values themselves as our outputs. Okay. So why don't you modify now your code to plot the t variable in one graph and the I1 variable in the second graph. And I'd suggest you can do this in a very naive way, just with a cut and a paste and a change of one line. Or you could do something more elaborate. It's up to you which way you want to do it. So why doesn't everybody try that? Is it clear what I'm suggesting as a little exercise? And I'll do it along with people. Again, you could do it more elegantly than the way I'm going to do it. So if you come up with a prettier solution, feel free. That's my solution. Not pretty, but it's a way of cutting and pasting. Again, I'm sure people can come up with a nicer way of doing it. And I should say that that's about the most, besides some array manipulation, that's about as much Python as we're going to need for this class. We're not going to be doing a lot of very elaborate Python. Well, when we get to parameter optimization, we'll do a little more Python. For most of the class, you don't need much. Because the whole point of this, the whole point of these kinds of modeling languages is that you put the heavy duty model, the heavy duty part of the model into the modeling language. And you just use the Python to do the displays and the time that the parameter manipulation. Okay, it looks like most people are done. Let me try mine. So here, I didn't relabel the graphs. Perhaps I should have. Here's one graph that shows the decreasing number of uninfected individuals. That's the the capital T versus time in the top one. And then the second one shows the number of infected individuals going up. Of course, the sum of the number of uninfected individuals and the number of infected individuals is constant. So it's not the most exciting graph in the world. But that's let me see if I can shrink this so it's a little easier to see. Okay, did everybody get something like that? Again, for people who've done this a lot, this may be going too slowly. For people who haven't used Python before, this may be going fast. I'll try to strike a balance between those two at the beginning, and then once people are familiar with the things we do, I'll speed up maybe a little bit. On the other hand, you should never be shy. If it's going too fast, please speak up and say so, and we'll slow down, because I'd much rather people play. When if that happens, in other words, if you're ahead of everybody, and you've done the exercise, sometimes I'll explicitly say, well, if you've done the exercise, go ahead and try this or this. But I hope that as time goes on, you'll come up with interesting things to try out on your own, even if I'm not suggesting it. So you don't just have to sit and wait. So for example, you might say, well, okay, we scanned the initial amount of virus. What would happen if we change the initial number of infected individuals and change that, try it out? So don't feel that you have to just sit and do nothing if you're done with the exercise. There's always more to do. Okay. So one thing that you have to be aware of is that this parameter of overriding is very convenient in Animony. And so you notice that we said S.M.V equals 10 to the P. And what that did is it replaced the initial value of V that we had specified in our original model with a new value. And there are a couple of possible traps here because of the fact that the antimony string is only parsed when we load it, it's not reparsed. And so if I wrote instead of writing m dot v equals 10 to the p, if I wrote m dot t naught equals 10 to the p, what would happen? Anybody want to guess what would happen? In my code, it says T naught is equal to 1 e to the 7th, and then T equals T naught. T is the initial value of the number of uninfected individuals. So if I write this, will it scan the number of uninfected individuals? Will it give me 1 person, 10 persons, 100 persons, 1,000 persons? Anybody want to try it? Why don't you try it? So one of the problems is that if I change the value of a parameter, and that parameter is used later on, it doesn't always change the dependent parameters. If I say T naught equals 10, I equals 2 times T naught, and I change T naught, it won't change the value of I. And that's something that you have to watch out for. If it's just equal signs, it'll work. If there are arithmetic changes, it won't work. And so it's safer if I'm going to scan it to scan the value of T rather than the value of T naught. In general, I'll try to steer you away from traps like that. In this case, it's okay because we only had equal signs. But there are a couple of places like this where there's some risk because the models are not read overwritten each time. Okay, so we mentioned the reset function. We used the function reset all on the simulation. There are a couple of other resets. If I do a reset all, if I change the value like m dot t naught equals something, that value will also be reset. It'll be overwritten. If I do just r dot reset, it will change the variables like a or t naught, t or I1, but not any parameters that were changed. And reset to origin, in principle, resets things even more. In practice, we rarely use the things that are different between reset all and reset to origin. So we typically always use reset all. There isn't a command that resets the parameters without changing the variables. Occasionally, it would be nice to have that, and we don't have that. Again, these are some of this may be some of these things maybe will become more obvious about why we need them as we go through. Okay, so now let's go back to thinking about viruses. And we're going to build a very, very simple model of viral epidemic. So we're going to do a little bit of epidemiology. This slide was built back a year ago when we were basically in the beginning of the second wave of the virus. And what we saw was that, at least in the first wave of the virus, we have this typical pattern of behavior where the viral load is very low. We see essentially an exponential increase of the amount of infected individuals. We see a maximum And then we see a slower decay. The world would have been happier if it had been more like Italy and then everything had gone back to zero, but it didn't go to zero. It came back up again. Again, sometimes you go down to a low baseline and you stay there. That would have been also a happier world than the one we live in other cases, you have annual peaks or like with influenza, twice a year peaks, which come back year after year. There are a whole variety of different patterns of viral infection. And in this simple model, the only thing we really are going to be able to do is reproduce that one shape that we've got here. But we want to think about why that is. So let's build a very simple model of an epidemic. And the simplest one we can build is essentially almost the same as the one that we've got already, which is called SI model, susceptible infected model. And these models tend to be named after the names of the variables. And so we'll have SEIR models, SIR models, and so on. S stands for susceptible. Somewhat peculiarly, usually the variable name for S is capital T. Go figure. I stands for infected. R stands for either recovered or dead, usually. And so we're going to begin with a model of a disease where you don't recover. So this would be a model of a disease where the infection lasts a lifetime. This could be something like HIV, herpes, many kinds of hepatitis. These days, hepatitis C can be cleared usually, which is new, relatively new and very important. It's not only viruses. Tuberculosis tends to be a lifetime disease as well. And so, of course, there's also the issue of infectivity. Very often people are infectious at a high level early on in the course of the disease and then become less infectious. That's not always true. As we know with COVID, one of the big problems with COVID is that you can be maximally infectious before you have any symptoms, which is why mask wearing is so important, because you often don't know that you are infected and you're going around infecting people. You can feel fine. Influenza is also a disease like that. Typically, you're at or near your maximal viral load before you start feeling sick. The flip side of it is that even with a lifetime disease, if you have things like for HIV, antiretrovirals, which reduce your viral load, even though you're infected, you could be very low infectivity. We're not going to think about those problems here, although if one were going to do mathematical modeling of epidemiology, those are things that are very important to understand. And there's some very famous people like Schiffer and Perlson who've spent a lifetime building these kinds of models for diseases like HIV. And a lot of modern treatment of HIV, for example, is based on those models. So these are places where actually the modeling really does make a difference in the world. But we're going to make the simplest possible assumption. We're going to assume that we have some population, I guess I'm going to call it S here instead of T, for susceptible. And those infected, uninfected individuals can become infected. And the rate of infection is going to be some function. And that rate of that function could be a function of the number of infected individuals and the number of uninfected people. There isn't really anything else it can depend on. And we're going to assume that basically the only thing we can do with two variables, S goes to I. We've already said people don't die, so they don't disappear. They don't recover, so I doesn't go off to do something else. That's all we got. So there really isn't much flexibility in this model. On the other hand, we have to have some hypothesis about what the rate of infection is. as a function of S and I. And the simplest assumption is the following. Suppose that our total population, which is S plus I, is S naught. Then the fraction of people who are infected, little I, is the number of infected individuals divided by the total population. You've heard probably of things like positivity rates for COVID tests. So that would be the equivalent of that. And we're going to assume for the moment that when you're sick, you don't change your behavior. You're not wearing a mask, or people aren't wearing a mask right. Now, in reality, probably when you get seriously sick, you are going to change your behavior. But as I mentioned, in a lot of cases, by then you've already had plenty of opportunity to infect people. So here is a little picture of somebody coughing. The red person is coughing. And that red person is going to go on and infect 2 people. And each one of them is going to cough and infect 2 more people. Each one of them is going to go on and infect 2 more people. And so we're going to get an exponential increase in the number of people who are infected. So that's the basic idea. Yeah. And we're going to assume that each time an uninfected person encounters an infected person, that the probability of being infected is just, sorry, I said that wrong. I said the answer before I meant to. When we have 2 people encounter each other, we're going to assume that the probability of infection is some constant. When you have an uninfected person in contact with an infected person. If I encounter somebody and I don't know whether they're infected or not, the probability that they're infected is just that little I. It's the total number of infecteds divided by the total population. And so we'll say that the probability of infection is just capital I divided by S naught. That's the probability per person. We have S people. So the total rate of infection then is going to be, well, we have one more thing we have to think about before we get there. So for each encounter, we have a probability that the person we're encountering is infected of I over S naught. We're going to say that the probability of infection per encounter is gamma. In a lot of the models we'll run into, we'll see a parameter called beta, which is going to be the product of gamma and n. And we're going to say we have n encounters. And the reason we're breaking it down this way is because if we do social distancing, what we're doing is reducing the number of people we encounter every day. If we're wearing a mask, we're reducing the probability that each encounter is infectious. And so even though it's the product that matters here, it's nice to have it call them out separately, because if you're thinking about remediation strategies, we would deal with those as separate problems. And we're going to assume that everybody mixes equally, that there are no cohorts. In reality, that we know there's a cohort, we're in the room together, therefore my probability of infecting one of you is much higher than my probability of infecting somebody who's out in the hallway. And my probability of infecting somebody at the university is higher than my probability of infecting somebody in Louisville. But we're going to assume that we're dealing with a population that's what's called well mixed, where we don't have to deal with that. And that well mixed assumption is usually not a very good one. And we'll find out if we try to fit experimental data, political data, that you get some sort of paradoxical things out of it. But is it clear so far what we're doing? And so the probability that I get infected, then if I'm uninfected, would be my number of encounters n times I over S naught, that is the probability that each encounter is with an infected person, and then times gamma, which is the probability that an encounter with an infected person infects me. Now, you could make an argument, which would be legitimate, that in fact, this is a discrete process, and that once I'm infected once, encountering somebody else who's infected doesn't change my status. And therefore, I should be using some kind of Poisson rule instead of a linear function. But we'll assume the probabilities are small enough that that's not going to make a difference here. And so in that case, the probability for each person in my population, each uninfected person in my population to be infected is n gamma I over S naught. And the number of uninfected people is S. So the total rate of new infections is S times n gamma I over S naught. So that is V of S and I is equal to I times S times n gamma over S naught. So n gamma over S naught is a constant. I and S are variables. And we could write this now as a pair of ordinary differential equations. The S by dt is equal to minus n gamma I over S naught times S. The I by dt is n gamma I over S naught times S. And you'll notice that's a little bit different from the equations we wrote down last week and worked with earlier today, because before the rate of infection was independent of I1. It depended on the number of uninfected, but not on the number of infected. Now, instead of having V in the numerator, in the rate law, we have I1, or in this case, I. And so we have a different functional form. All right. So now let's do a very simple exercise, which is take the simulation that we just wrote and modify it now to run this rate law instead of the one that we wrote before. Why doesn't everybody take a minute and do that? And let's ask the question, what does the result look like compared to the one that we had first? How is it different? In particular, you might ask the question, how long does it take for half of the population to be infected? And you need to have some parameter values. So let's assume that you have one encounter per day. That would be actually pretty strong social distancing. We'll assume that we're going to have a population of 1 million people to begin with. The probability of being infected for each encounter with an infected individual is 0.1. And let's start out with one infected individual. So 1 million uninfected, one infected. Or if you want to be more careful, 999,999 uninfected, one infected. And one thing you have to watch out for in antimony is reserved words. And it winds up that gamma is the gamma function rather than a variable. So don't use gamma. If you use gamma 1 or GMA or something, or G, that's all right, but don't use gamma. Okay, is it clear what to do? And again, I'll type my own version of this. And we can see what happens. You may do it faster than I do. Okay. Okay, if anybody needs help, let me know. All right. Oh, thank you. I made a mistake. Very good. As I say, that's because I'm typing, it doesn't mean it's right. I do. It looks like I made another mistake too. Let's see, what did I do? So at least when I run this, I get nothing. And the reason I get nothing in my case is that it takes a very long time for it to do anything. And let's see what I had in my solution here. Oh, I set n equal to 10 instead of n equal 1. So if I have one encounter per day over a time of 10, that would be 10 days. I effectively have no infections. If I increase the number of encounters per day from 1 to 10, let's see what I get. Things are just starting after 10 days. And so now I have to make my model last a little bit longer. You got something like that. Did people get something like that? Does that work for you? Did anybody get something different? So there's a question in the chat. The question is, you need a semicolon after the number. The answer is that in Antimony, you have an option, which is you can either use a semicolon or a carriage return to indicate the end of a statement. It's good practice to put a semicolon at the end of every statement, whether you have a carriage return there or not. So the answer is that if I typed it, this way, I don't need a semicolon. But if I wanted to put this all in one line, like that, then I need a semicolon. So those are equivalent. So thank you for catching that. So I've got two people who are more on the ball than I am. So both of you caught my error. So let's look at the results of this simulation. Notice that I used n equals 10 here instead of n equals 1. If I did n equals 1, let me come back to the one I originally asked to do, n equals 1. N equals 1, even at time 30, nothing has happened. If I go out to time 300, then I get the infection. It takes a long time. So if I start out with n equals 1 encounter per day, then the infection and one infected individual, then the infection doesn't really take off for about 120 days. And so a lot of the exercises that I'm going to ask you to do in this class are going to have the question, describe what you see. And I realize that at the beginning, that seems very vague and maybe is frustrating. There's a bit of a trap in that, in the sense that if I'm very specific about what you should see, then I've given you the answer. And I'd also like people to try to develop some intuition about what to look for. And so let me tell you a little bit about what I'm looking for. If I ask you for a picture, if you get a picture like this and I say, what do you see? Let me try to give you some pointers about what it is you might want to identify as things you see. And sometimes in the past, I've given an entire lecture on this topic. And I realize that often, I mean, people's eyes may glaze over when I give this lecture, but when I give that lecture, people's eyes really glaze over. Because until you've experienced it, the abstract question of what you should describe doesn't make any sense. And so I'll try to do it in the context of what we see here. So something that you might look at, you have two curves, and one is one minus the other, and the population minus the other. So really you only have one curve. And this curve isn't doing very much. My initial population, let's focus on the infecteds. My initial number of infecteds is very, very small. It stays very, very small out to about 70 days. Then it goes very abruptly up to be nearly 1. And by 150 days, essentially everybody's been infected. And so you can ask the question at short times. What I'd recommend doing is looking at this time series and ask the question in a sense, ask the questions that people asked back in March of 2020 when this whole thing was getting started. There were a few infections, and you wanted to know, were there a lot of people infected to start with, or only a few people infected to start with? So ask the question at the beginning, here I set the initial value of one infected individual. So you'd say, how many were infected, uninfected people were there at the beginning of this thing? Then after that, I would say, what is the change of the population? In this case, at early times, the slope is almost zero. There are very few people being infected. And so if you were back in March and there were a couple of infected people in your city, and you looked at the rate of new infections, you'd say, boy, this is nothing to worry about. And so that would be the first thing I notice, is that slope at near time zero, positive. Well, it's positive and tiny. Negative or zero, it's nearly zero. So the number of infections is near zero, the rate of increase of infection is nearly zero. Then I would jump to the far end, to late times, and ask the question, does the value keep increasing? Well, if you have a finite population, it can't increase to infinity because there's a limited number of people. Does it reach a steady maximum? And how does the steady maximum compare to where the other one started? So in this case, the result is pretty straightforward. All of our uninfecteds become infected. So the number of uninfecteds goes to zero and stays there. The number of infecteds goes to one, or the total population is zero, it stays there. But if we had recovery, we could have something else go on. So this isn't the only kind of output we have. And so what I'd ask then, that we notice that everybody gets infected. We basically switch. We're going to very soon run a simulation where not everybody gets infected and where the shapes of the curves are more interesting. And then when we've looked at what happens at early times, at the beginning, and what happens at late times, we look in the middle and ask the question, what's going on? And really, there are only two features that matter in the graph of the one that we've got here. And that is, what time did we get to half of the population infected, which is about 120 days here. And we could ask, what's the slope? How steep is our curve? And so we could now run this simulation again. Okay, and we could run the simulation again and ask how it changes. And let's just change the number of encounters that our individuals have. Instead of encountering one person per day, we're going to encounter two people per day. The initial values and final values are the same, but instead of having half the people infected after 120 days, we have half the people infected after 60 days. And the slope is steeper. What would happen if I go back to my N of 1, and I say my initial number of people who were infected was 1,000 instead of 1. Notice now that shifts the time axis. Effectively, that's shifting the time axis. And so now the slope is the same as it was in my first simulation, but the time to half infected is about 45, 50 days. There isn't that much else you could do with this simulation. There really aren't that many things you can play with. Okay. And so the next thing that we might want to do is basically a parameter scan. And now we're going to have to deal with a little bit of Python. And when we do parameter scans, the first way we did it was we plotted the same thing again and again on the same plot and then displayed the plot. But sometimes we're actually going to want to be able to manipulate our plots in more ways. In particular, suppose that we wanted to plot, and this is going to be a homework assignment, we wanted to plot the time at which half of the population is infected, not as a function of time, but as a function of the parameter. So we're going to change the parameter value, we'll measure something, we want to plot it versus a parameter. In that case, we have to use the matplotlib functions. We're not going to be able to do, we're not going to be able to use the built-ins. And so we're going to have to learn how to deal with this data output array S that we get. And I'm going to give you a little bit of basic NumPy array, NumPy and array slicing. And if you're used to Python, you'll be very familiar with this. If you're not used to Python, it may get take a little bit of getting used to. The S is a NumPy array with this extra line, this extra header row in it. And so if we have a NumPy array and we have square bracket index, that'll give us the row of the array. And if we put a second square bracket after that first square bracket, that'll give us the column. And everything is zero index. So if I go S square bracket index, that gives me row S plus 1 of the array. And then square bracket 0 gives me column 1, square bracket 1 would give me column 2, and so on. So if I say M equals R dot simulate, and I ask it to give me time and I, that's going to give me a 2-column array. And if I go ask it for M sub 1, that will give me not the first row, but the second row, the time after one time step and the value after one time step. There are a lot of these functions we could use. And as you may know, with Python, you can also do what are called iterators. So if I do M square bracket colon, that'll give me the whole list of things. I could do M square bracket 1 colon 17, and that'll give me a piece of it. So let's do that here. Let's iterate through the array and find the time at which the number of uninfected individuals is decreased to half of its initial value. And if you're used to working with Python arrays, this will be familiar to you. If you're not, I can go back, I can scroll back by one and show it to you again. And if you're very NumPy-y, you may actually want to use their NumPy has a variety of lookup operators which you could use to give it to you without iterating through the array. But up to you to decide. Okay, is it clear what I'm asking you to do? So what I want you to do, on the cursor again. What I'd like you to do is, I guess the answer is probably so small you can't read it here. I'd like you to iterate through the array and then print out the time at which the value is half its maximum. And again, there are some lookup operators in NumPy that you could use to give that to you immediately. But I'd like people to, you're welcome, if you're sophisticated, you're welcome to do it. It's fine to do it in a naive way. Somebody said, 2 people say they're done with the exercises and a couple of people need more time. If you're done with the exercise already, why don't you create a little bit of a challenge for yourself and create a plot which scans the number of encounters per day and then plots the number of encounters per day versus the time it takes to get to half of the population infected. That winds up being the homework problem. So if you jump ahead and you've done this already, then you've got your homework problem done. If anybody online needs help with that, let me know. It might be helpful to remind yourself it might be helpful to remind yourself here. To remind yourself here of actually what the simulate object looks like. You might just want to print S so you see what it looks like. Here is that complicated, that array structure. And if I type, for example, time, comma, uninfected, that's what the array looks like. So is there anybody in the room who has not ever done array slicing in Python? Everybody says they've done it. So in that case, I hope it's not too demanding. I did it in sort of a brain damaged way. Yeah. Oops, type. Okay. So there are a lot of perfectly good ways of doing this. The way I did it was very naive. I set a index counter 0 to begin with. I created a while loop so that if the value of the population that's uninfected, that's S of index comma of 1, that's the second column. The second column, row index second column, is bigger than half of my initial population, then I read the time from the first column and I increment my index. And so that loop will exit when the value of the uninfected population switches from above 1/2 to below 1/2. And it'll exit with index pointing to the row at which that happens. And then I print the row number, the time, and the value. It's not going to be perfect because we're not interpolating. And so depending on how many points we have, we might be off by a bit. So in this case, it came up with a time of 16.45, 16, index of 16, a time of 45. And if I look in my plot, 45 is about right for half. You could do that a lot more elegantly with some of the search functions. Somebody is asking for help. Speak up, please. Who needs help? Is there a question? Try again. Question? Okay. If you'd rather type it in the chat, feel free. Okay. So that's the basic structure, the kind of structure that we're going to use. And we'll use that pretty often. Now again, you can use some pretty nice methods in NumPy that'll find array elements with particular properties without having to loop outside. I could have iterators where those arrays have iterators inside of them. I can have conditionals in those iterators. So I could actually put all of that looping inside of the argument of the index. For the purpose of teaching, I'd rather stick to something simpler, but certainly in homeworks and things like that, if you want to be more elegant and Pythonic, please feel free. If I suppose now I wanted to change my value of S naught, and let me do that here by hand. I change my, well, let me change, instead of S naught, let me change the initial value I. We'll go back to 10. Okay, if I go to 10, now the time to get to half was 90.99, so 91. So suppose that I wanted to sweep one of these parameters, for example, the number of initial infected individuals, or the value of n, or the value of gamma 1, and I wanted to plot the time as a function of that. I could certainly write a loop that will change the parameter and run the calculation again and again. If I want to plot it, I have to assemble those outputs into an array. Array manipulations, again, I wonder sometimes why Python didn't include the equivalent of NumPy arrays by default, but it doesn't. So let's now sweep S0 by factors of 10. and see how the time to get to half of the population infected changes as I change S0, okay? Why doesn't everybody try that? I'll reset this. I had initial infection of 1. Everything else is as it was before. And now the assignment basically is to add a loop around this that changes the value of S0. And again, one thing that you have to notice is that if you change S0, it doesn't necessarily change S. So you're going to have to change both. And the question is, does the time when half the population is infected change or not? Does everybody have that? So I'll give people a minute to work on that. And again, I'll do it myself, but try doing it on your own. Before you look at what I do. Just because I did it doesn't mean it's right. Now I haven't followed my own advice about being careful, so I'm going to try this and see what happens. And as I advertised, it doesn't work. Because I have to set S as well. Again, I'd prefer to let people try it on their own. If you've got it done, again, you could try writing it something that here I'm just printing the values. You could write something that's going to plot those values if you're done with the basic exercise. And if people are done who are done with it, does the time change or not when you change the number of the total population? Did somebody get it? Somebody says it does. Yeah, changes a bit. If anybody needs help with this, please feel free to speak up. Otherwise, I'll give people a few minutes to try it out. Again, you can copy my code, but you don't have to. You certainly don't have to use that. There are plenty of ways of doing it. I essentially, all I did was combine the code together. The thing that's tricky, which is why I've got this red note here, is that I have to do this. Changing the value of S naught does not change the value of S in the simulation. Because S's dependence on S naught is determined at the time of parsing. And since I'm not reparsing it, when I make the change, it doesn't update. There are ways to tell Antimony to force it to make those updates. I mean, people who are used to Python or C are used to there being different equal signs. One is for assignment and one is for logical comparison. So Antimony has two kinds of equal signs, one of which is a parser equal sign, where it's an assignment that's done at parse time. And the second one is a dynamic equal sign that says that whenever the value changes on the right-hand side, you update the value on the left. I'm not going to show that yet, but we'll get to it. There's some slightly tricky things about using that dynamic sign, which is something, but I don't want to do it right now. So my answer here was that it changes, but not very much. I don't know why I wrote no. It does change a little bit, but not a lot. So now, instead of scanning S, why don't we scan the number of infected individuals at the beginning? Something that I should have shown is the graph, because I didn't really show the graph. The graph here is not very pretty, because when you change S in powers of 10, you really only see the top one or two. Most of them are too small. So now the next exercise is only a one-line change here. That one-line change is, instead of scanning S naught, scan I. So now you want I to be 1, 10, 100, 1,000, and so on. And so we can do that here. We just change the initial value of I. We have to be a little bit careful to make sure that 1, 2, 3. I have enough zeros. 1, 0, 10, 100,000, 10,000. Actually, I'm missing a zero. So I'm going to scan I instead of S. You guys can do the same thing. And now I've got to print I. This one's actually going to be a little bit, I have to save that value of I somewhere because it's going to be lost if I want to print it. Again, it's probably better that you do it on your own. But try that. See if that works. Works for me. Okay. What did people get? Remember that when you change the initial number of infected individuals, effectively you're moving time later, but the dynamics don't change. And so what I've done here is, as I increase the initial number of infected individuals, the time at which half of the people become infected does to be shorter. And you'll notice that a 10-fold increase in the number of initially infected creates the same interval. Because we have exponential growth, effectively, what we're getting is that the time is the logarithm of the number of infected individuals. But all I'm doing is shifting in time. Okay. So now suppose that I wanted to take this set of results that I have here and plot them. There are a lot of different ways to build a plottable array. None of them are that pretty because you don't have, well, if you know exactly how many rows and columns you have, of course, you could do something that's like Fortran or C++, where you declare an array and you do it. Very often when we're doing things here in simulations, we don't know how many rows or columns we're going to have. And so what we're going to use are the NumPy VStack and HStack commands, which are not, I think, anybody's favorite syntax. But they allow you to build a, typically in Fortran, in the old days, you couldn't change the array shape. Once you declared it, you were stuck with it. C++ lets you change array shapes. Python and NumPy have a classic idea of an array shape. And so one thing that you have to worry about in Python is that you can't operate on something that doesn't exist. And so probably the single most confusing thing to deal with about NumPy arrays in Python is that you have to create an empty placeholder one to begin with before you start doing things to it. And so what we'll do when we're going to build arrays typically is we'll start out by creating an empty array placeholder. In this case, we're going to have two columns. The first column is going to be our parameter value. The second column is going to be the time. Yes, you could do it. as Juliana says, yes, in modern Fortran, if there is such a thing, as of 1977, you had allocatable arrays where you could change the size of the array. Yes. I'm old enough that I predate Fortran 77. Scary. So the fact that you know that about Fortran is already scary too. But okay, so we're going to do NumPy array, and there are a lot of options for doing this. As usual, NumPy. The one that I like to use is NumPy empty. And NumPy empty takes the argument shape, and then the shape gives you in curly brackets, in regular parentheses, the number of rows followed by the number of columns. And in this case, we actually don't want there to be any rows, which is sort of an odd idea, creating an array that doesn't have anything. It does not only is empty, but has no rows. But we're going to do that. That's very Python-y. So we'll set the result equals np.empty, shape equals 0, 2, creates a placeholder, a container for a 2-column array, an empty container for a 2-column array. And then we can use vstack. And vstack is going to act as a method acting on our array. And it allows us to combine arrays vertically, to glue them together. And so if I have 2 arrays and I want to combine them, if I say result equals np.vstack, and then somewhat confusingly, I have a lot of square brackets. I have a regular parenthesis, and then I have a square bracket, because it's a list. And the first element of the list is the thing that I want to put on the top. And the second element of the list is the thing that I want to put on the bottom. And so here, if I'm adding a specific line, I have result, which is my array, comma, square bracket, the value of my parameter s, and then some second column. It could be, I could have, say, 2 arrays, array 1 and array 2, that I'd say result equals np.vstack, parenthesis, square bracket, array 1, comma, array 2, close square bracket. And this array I can plot using the TE plot array function. Right. The thing that you have to remember when you're doing a VStack is that the number of columns in your arrays has to match. If I take an array with 3 columns and an array with 4 columns and try to VStack them, it'll crash. All right. So that's one functionality we want to know about. Another one is that so far we've used integer iteration and we've gone by powers of 10, but typically we're not going to want to do that. Basic Python doesn't have iterator like for I equals 1, 15, 0.1. Again, I don't know why they didn't put that in. That seems like a pretty obvious thing to have had. Well, I do know philosophically why, but sometimes philosophy isn't so convenient. And so we have to use the NumPy A range, which behaves the way we would expect, where you have the start value, the end value, and the step size. And these are floats rather than integers. And it's actually sort of important that you remember the point zeros if you have integers and you don't want, because you need to have those 2 floats. All right. So now our next exercise is going to be to take our printout and the NumPy functions we just talked about and use them to create a plot of this printout. We're going to have the first column be the value of our parameter, and the second column be the time at which we've gotten to half our maximum value. So we can take that loop that we just wrote, and instead of just printing it, what we want to do is we want to append, using VStack in this case, append. You could use an append also if you preferred. Assemble that into an array, and then we'll use the plot array function to plot it. Okay. So why don't people take a minute and try to do that? If there are any questions about that, or is that a clear exercise? And I actually haven't shown you the exact syntax for plot array, but if you like, you can look that. That's on the cheat sheet for Tellurium, and it's also in the manual. Or you could use the matplotlib plot array too. I'll let people spend a minute or two thinking about it on their own before I start typing. If you don't know how to plot your final result, that's okay. Try to just assemble the matrix, and then you can print the matrix out, see what it looks like. One of the things about the way we're going to do things in this class is that I'll try to build everything very gradually, and we'll use the same little functionalities and code snippets again and again. So once you've gotten the experience of doing one parameter scan and plotting the result, if I say, okay, now scan a different parameter, it shouldn't be too bad to do it. And so once we have a couple of these basic modules, finding a value in an array, finding the index of the value in an array, which is what we did here, and then plotting it as a function of a parameter. These are things we'll do again and again in various permutations. And so once you have code that works for one, you'll be able to reuse it. So I do recommend, and if you have code that you like that does it better than what I've written, and I think many of you probably who are more experienced in Python can come up with more elegant solutions, please remember to save it and download it so that you have it available. Because if we're doing these things today, I guarantee it'll be in the homework to do it. And I also guarantee that you'll be asked to do the same thing on different models in the future, because throughout the course, we're going to be analyzing what happens to the model as we change parameter values. And we're going to be asking questions about when does something happen, or how big is something at a given time, or how big is something at its maximum value. And so once you've written a little function that does that, you'll use it over and over again. If you want it to be elegant, we could wrap things in Python functions and define functions that do these things. Or we could look up in the NumPy manuals and see if they've got a predefined function that does it. But most of these things are simple enough that implementing it by hand isn't that bad. So I'll give people a few minutes to work on that. In terms of array operations, I typically won't do anything more complicated than VStack and HStack. Again, there are plenty of fancy ones that you can use. And you'll never believe me, if you look up in NumPy and say, gee, there's a beautiful NumPy call that does this in one line, by all means, share it, and we'll share it with the class. It helps if I load NumPy. Okay, we'll give people a little more time. If people are done with the basic exercise, you could change the range from, instead of doing a fixed integer range, you could use the A range, NumPy A range, to do a smoother fit. Well, not real pretty. Because the simulate doesn't have enough points in it. Another thing is if you're getting an ugly result, it may be because the number of points in your simulation isn't enough. It's not smooth enough. So you might add some points to your simulator. And again, there are many ways you could implement this exercise. I'm just showing one. And if this is something that's unfamiliar to you, you might, it's fine. We're not, as I say, we're not going to do too many different things. There are only going to be a couple of things we need to do. So you might practice using these methods a little bit, sort of set yourself a couple of simple exercises to try out your ability to manipulate matrices. And if you're sophisticated and have done this a lot and you want to look up and come up with more elegant ways of doing the same thing, that's fine. And again, I'm happy to share those with everybody if you come up with a particularly nice way of doing it. I'm going to typically show you what I think of as, for me, the simplest possible way of doing it. That may or may not be the most elegant way of doing it. Okay, so what did I do? The first thing I did here was I had to import numpy as NP, which I said we should always have. And then the next thing that I did was I created an empty array here before I started my loop with 2 columns. And then after I printed my values here, I added to this matrix that I created using the VStack matrix is the existing matrix. And then at the bottom of it, I add column 1, the value of my parameter, I0, and column 2, the time. And I also had to save that initial value of I, 0, the initial value of I, because that'll get overwritten. Because the value of I changes in time, so I don't know what it was. I could have used 10 to the P here. And I also used an A range so that I smoothed out my, my plot. If I just did 6 points, it would be pretty rough. So here I did, I don't know how many, 660 points probably, it's 59 points. And here's what my plot looks like. As a function of the initial number of infecteds, the time to get infected, if I start with 1 infected individual, is about 140 days for half of the population to get infected. It goes down very rapidly till it reaches about 40 days. And then as I keep increasing the number, the time goes to 0. And here I've actually started with more infected people than I had uninfected, so that doesn't make any sense. So did people get something like that? Did people get something like that? Did they get something different? Did people have a better way of doing it than that? Okay. Okay, so I used a plot here. I used the function TE plot array. And that's a Tellurium method that will allow you to plot arrays. It can also plot the output of a simulate just the way the other one does, but it doesn't by default plot the axes and everything else the way just the plot does. And so it gives you a little bit more control. And this is what I just did here. So that's where we got to. So when you're going to be using plotting arrays, you may also want to be able to plot multiple things in the same plot against time. And there are a variety of ways of doing that. If you want to be consistent, the way I often do it is the following. I will create an initial array which just has the times. And then I will use not VStack, but HStack, which combines matrices in the horizontal rather than the vertical direction. So it attaches things by columns rather than by rows. The problem again with all of these stack commands is the shape of the matrices has to match. And so we'll find that very often we want to have a column matrix which consists of our times. And it's sort of a waste of computer time, but one way to get that easily and not have to worry about all the rows lining up is to use m equals r dot simulate, whatever the simulate command is going to be, and then just put out the times. And then if I change, say, if I had 150 points or I went from 0 to 30, it will do it all correctly. And that'll give us the time column that we need for doing our plots. Then if I run again, and I say that was m equals the time, now I run n equals r dot simulate, and now I just put out the value without the time. I now have a column of the values. And now I could use HStack to put them next to each other. So this is a little bit, maybe seems like too much to do, but if I said array equals n pi HStack of n comma m, where n had, sorry, m comma n, where m had the times in it, and m had the value, then that would have been equivalent to doing a simulate where I printed out time comma value. And you can argue that that's not doing very much. It's made a mess of something that was pretty simple. But it's actually sometimes if you want to stack a lot of things together and you don't want to plot them, do it by overlaying the plots, that's not a bad way to do it. And so let's imagine then that we're going to do a parameter scan here, and we're going to plot the time series. So here, what we're going to do is we're going to write a sim loop where we say m equals r dot simulate 0, 20, 100 time. That'll give us a column of our times. And now we're going to scan, say, the initial value of S, the initial number of uninfected individuals, between 0 and 10, steps of 1. I reset my model. I set my initial value of S. I now run the simulator. I just pull out here one of my values variable. And I add, each time I run it, I add it on the right-hand column of my array. And so my array gets deeper and deeper and deeper. And the nice thing about doing these kinds of array extensions is that if I don't know how, if I did it with a fixed matrix, I'd have to know how many rows and columns I needed. Here, this will build the right size automatically as I change my parameters. So again, that's one of the things that we might want to be able to use. Another one that we might want to be able to use is, which you've already done, is that we use the show equals false option. And we use the show equals false option a couple of times and then showed the plot at the end. Here's one here where we did that. And one problem with that is that all of the lines are the same color. And so plot array has an option for changing colors, and it's sort of weirdly named because the default is not to show the colors. And so there is a command called reset color cycle. I have no idea how they came up with that name, which is normally true. And if you set reset color cycle equal false, each line will have its own color. Now, in fact, it won't all have its own color because it has a limited number of colors and it'll keep going around. But you could try that and see what it does. The other thing is that, and this won't work for the example I did because there are too many lines. You can also, that little key that we had in the default plot function where it labeled by the name each thing, we can define a key for the plot. Again, if you have too many lines, it's not going to be very pretty. And that is using the command labels equals and then a list, which is the parameter, the label that I want. And that label has to be a string. And so if I want to say plot the number, I have to convert the number into a string. So if I said I want to label each color, each line by the value of the parameter, I could use label equals square bracket string of parameter value, and that should work. And so why don't you try that here. So what I'd like you to do is take this example that we have here. I'm going to change it back so you're not plotting so many. Let's just plot 6 or 5. And now in my plot array, which I actually have to do here, I have to actually change this because I have to use plot array. All right. Now I have to, if I use plot array, I have to give it the argument, which is the matrix. And then I'll use show equals false. I'll set the color cycle to be false. And then let's run that and see what that does by itself. Oops. Give me a typo. Yeah. What did I do? There's attribute there. Oh. That was funny. I managed to type resent color cycle instead of reset color cycle. So reset color cycle is false. Bad choice of variables. I tried to do too much here. I should have done the one that I had. Let's see. Let's just actually type exactly what I have here in the district. Okay, we'll do a loop. A naught and n pi a range 0, 4, 0.5 r dot reset. I'll run my simulator. Sorry, this is a different, my mistake here, because I've got a different example here in the screen, so I have to invent something on the fly. Does anybody want to try to invent something on the fly for this? People are tired, probably. We're almost at the end of class. The example I have here is slightly different from the one on the I apologize for that. Let me go back to the one we have here. Load model. That one we don't care about. We'll do 6 values. That's fine. M dot I equals 10 to the P. That's all right. I0, okay, fine. S equals M dot simulate. That's all right. And now we're going to do a plot of S. So equals false, color cycle equals false. T show. I see what happened. So I've got, and then I do T plot array. Should be. All right, why is it not plotting? Juliana, do you see a bug?
Not seeing anything obvious.
Why am I not getting? Let me restart your output. All right. Huh. All right, well, I guess we will have to figure out show color cycle next time. If anybody sees the problem, that would be great. Yes. S equals m dot simulate. P plot array, S show false, C set color cycle, T show. Okay, let me try. Let's try doing it the way I got it here. Plot array. S instead of show. Okay. So unfortunately, it looks like the TE plot. So it looks like the TE show doesn't operate on plot array. To show the plot array, you have to use plot array. All right. So everybody is probably tired, so that's enough for today. This should give you everything you need to do the homework. The coloring and labeling is a bell and whistle. You can look it up. It's in the manual. I don't mean to spend a lot of time on it. And I apologize if I messed that one thing up. So are there any questions before we break? I'm sure people are tired after 3 hours. So was that the version of this that was in, was that the Word version of it or the version in Canvas? Okay, so one thing that I think I said, which is that Canvas, was that the Canvas assignment or was that the version of the file in Canvas? Okay, so something I should have said back the first class, and I will say now, and I apologize, especially because that homework assignment assumed that we had done this first exercise here today. So if you run into a homework assignment, I will normally try to update the homework assignments based on what we covered, because I don't always know how far we'll get. If for some reason I don't do that, please look at it and say, we didn't get that far, and assume that that problem will be assigned for the following week. So I should have said that last week, and I apologize. I think I sent out as an email a revised version of the homework assignment. Did you not get that? Okay, because I thought I had fixed it, so we didn't have that. My mistake. So if there is something that we didn't cover, you have two choices. One, you can play with it and assume that we'll cover it in the next class, in which case you're very well prepared. Or you can hold on to it and hand in the homework the next week. So that's because, as I say, I don't always know exactly how far we'll get. The second thing to be aware of is that while I will put the assignments into that Canvas assignment, that the way Canvas posts assignments, formatting is a bear. And so it will often eat equations, figures, and other things. And so the official version of the assignment will be the one in the Word document. And I will try to upload to Canvas a Word document that says homework number 1. And I will also always have in the Google Drive something that says homework number 1. And I will also try to email to you a PDF or a Word document called homework number 1. And so if there's a formatting error or missing information in the Canvas listing, assume that that's because Canvas strange formatting system ate it. And I appreciate, thank you for bringing that to my attention, and I appreciate your patience that I should have said that last week. Well, I'm sorry if I wasted your time. I know you've got a lot of things on your plate and I don't want to waste your time. So thank you for bringing that up. I'm sure that everybody will run into that kind of thing. And definitely there could be typos in the homework. So even though these homeworks have been gone through in previous years, that doesn't mean we catch everything. And I'll often try to adjust them to make them more appropriate. And of course, sometimes when you make the adjustments, you introduce new mistakes. And so I do appreciate your patience with that. Thank you for bringing that up. And again, well, I have the comment that, I really want the homeworks to be handed in on time. I also recognize that things happen, people get sick, things come up. And so if there's a homework problem that you feel wasn't appropriate for the week, just hold it and hand it in the following week.